Thank you. So what I'll talk about is during the course of Lue Pan. But we also repeat crucial help from nothing also. Let's talk about that thing. So, all right, so here we're all interested in studying fundamental groups. So suppose I start with logical space. Well, let's say it's that connected. So I'm interested in understanding its fundamental group. And I want using the ideal corner term, so it means that I understand fundamental group in terms of its actions on other things. So in terms of its homomorphisms to other groups and transformations. So if I'm interested in homomorphisms into abelian groups, right? This is an abelian group. Then I know very well what this is. This is just the first cohomology of my space. Coefficients in that abelian. All right, so there's a direct relation between representations of y1 into abelian groups and but suppose I'm interested in something more sophisticated, or maybe I'm interested in homomorphisms from y1 of x to some non-abelian groups. So can I relate this to cohomology? So for instance, suppose I have a representation of the fundamental group into an SL2 R. Right, R being the real numbers. So out of this, I can produce the following invariant. So if I have a homomorphism R, notice that SL2R has the following cohomology class. So I can look at the over here. So I can look at the universal cover of SL2R. This is a logical space. And remember that SL2R is homologically equivalent to a circle. So its fundamental group is Z. And the universal cover of a connected Lie group is always naturally a Lie group itself. So this is an extension of SL2R by Z, the generator in this. So let me just treat this as an abstract central extension of groups. So SL2R has natural extension by Z, so it means that there is some natural class, which I'll call E, in second homology of SL2R with Z equivalent. Right? Just a class of this extension. But that means that whenever I have a representation of the fundamental group of a space into SL2R, I can pull back this cohomology class, right? Because cohomology of cohomology of SL2R that's back to the cohomology of one space. Sorry, I'm going to squeeze this in here. I'll define the class E of to be the pullback of the class E under row. So I produced some invariant of such a local system living in H2 of X with Z coefficients. All right. And well, how good is this invariant? Well, let me first of all try to demystify it a little bit and let me relate it to something that you probably have thought of already. That well, another way of thinking about this invariant is as Euler class of the corresponding vector bundle. So E of prime, the Euler class of the vector bundle, the rank the vector bundle associated to this representation. Right? Whenever I have a representation, say real representation of the fundamental group, I can create a real vector bundle of the same rank on my space. So I can take the trivial rank 2 bundle on the universal cover. This is the universal cover of X. And I can quotient manage the active fraction of the 1 of X, where here it acts because it's universal cover, and over 2 it acts for the row. There's going to be a rank 2 bundle associated with this representation. And since my representation has trivial determinant, this will be a canonically oriented bundle. So I can take it to other ones. And back to the place. But now, well, I'm interested in studying these homomorphisms, and so I produce for you an invariant on this point. So how good of an invariant is? It turns out this is the best it can be under these circumstances. So here's the theorem. So the first part of it is integral for loop. The second part of it is p-adic. And the theorem will be purely topological, or in fact, the group theoretic, but the proof I know of it, it's really using another Boolean function. So my topological space is a surface of some use. That's good. It's a compact oriented homogeneous. then the second cohomology in which my class lives is just Z. Cohomology, dimensional variety. So out of such local systems, I'll just produce an integer. So what can this integer be? This is an equality proved by Milner that for any row, the associated class, well, it will be an integer, but it's sort of it depends on how I chose this orientation of this Z. So it really maybe only will define that up to a sign. But the absolute value of this here for is always supposed in G minus 1. Let me see that G of these two. So that's what's called Milner-Wood inequality. That you can't get an arbitrary number if you came from such a representation. But moreover, I was claiming that it's a good enough invariant. Well, it doesn't fully recover such a representation for the reasons that you see. I said that row really only depends on the associated vector bundle. So if I deform my rows a little bit, then the vector bundle is not going to change. So the class wouldn't change either. But up to that, it turns out that it's a perfect invariant. So if I map from local systems, so from all representations, well, again, I'm interested in isomorphism class of sign, considering this topology you see. Well, I'm just mapping to integers from 1 minus G to G minus 1. Then this is going to be a projection of connected components. So you can tell if one representation can be deformed into another by looking at this. I need to make one caveat here because I just chose to work with myself-dark rotation simplicity. I need to also allow here to twist, twisting by convergence from my fundamental group to plus or minus. Little caveat for it. Because it's through test central. I could make a statement linear if I consider representations to p-adic. Let's not worry too much. All right, so this is a nice invariant. Let me try to put this in a slightly more general perspective before I'll move to the p-adic world and I'll try to explain what I think is a p-adic element. So, well, why am I interested in creating invariants of local systems? Well, for instance, because one source of local systems, which I would like to apply these invariants, is monodromy homology of families of varieties. So let me imagine that X with elements of a great variety. And I have a, let's see, C local system. Which underlies the ratio of vectors. A polarized ratio. Well, pretty well, let's look at this monodromy representation. Well, since it's polarized, a priori, if I just have a local system, this would be a representation to GLSC or some kind. But since it's polarized, it preserves the Hermitian metric of this vector space. So it's actually a representation of some unity. So it's a group of isomorphisms of n plus n dimensional vector space equipped with a Hermitian pairing of signature and n. All right, so this is just recording. This is corresponding to. And so what kind of invariants can I cook up out of such a representation? So notice that this was analogous to, this was a generalization of what I was doing before because it has some to our is SU101. All right. So then what can I get out of such a class? Well, you see here the origin of my classes was cohomology of this group. And I don't really know how to fully compute the cohomology of this abstract group of coefficients in Z, but let me give you some slightly cruder invariant, which we know how to compute fully. So let me be interested in cohomology of this group with coefficients in R. And it's a topological group, so I'll just remember the Bolo unit. So I'll think about continuous. Well, I can to just define these logical groups, I can define its group cohomology using the standard bar complex, but I'm only going to use continuous cochains rather than arbitrary cochains. Right? So be aware that this is different from cohomology of the classified space of it. And if I have a class here, then, well, of course, I can restrict it to get a cohomology class in X, even if it wasn't continuous. But if it is continuous, then it's something called Van isomorphism, which completely calculates for me this cohomology. And so let me write down an answer, and then I'll explain how you might guess such an answer. So it's generated by classes C1 through Cn, and classes C1 prime through Cn prime, with the condition that the degrees of the classes with lower index I are 2I. And there is one relation, well, it's a graded ring, so it's a reduction. That's the relation that's give you several like y on every degree. So what is it saying? So this is responsible for characteristic classes of representations into U and M. So suppose I have a representation of fundamental group, even of any topological space into this group. I can look at the corresponding complex vector bundle of rank M plus M. And because of the signature conditions, we actually decompose into a direct sum of a rank M bundle and a rank M bundle. So I could look at the Chern classes of these two bundles. But also, altogether, they form a rank M plus M bundle, which by definition has a flat connection because it came from a representation of the fundamental group. So the total Chern class should better be trivial, which is why I'm killing by this model, because you have to support this to. Oh, sorry, yeah, thank you. Not to zero. Because if you give it a bundle that has flat connections, total Chern class is 1. Yeah. All right, and then, well, the trivial part of the Van isomorphism is that this is, in fact, this is all the classes you will get. And so out of this, if I started with this L, I could look at these classes CI with rho L, CI rho L, eliminating the cohomology space.
Can I ask a follow-up question? So the ring is often familiar to the rings to the cohomology of Rosmania.
It's not a coincidence, yeah. It's well, it's you can maybe naturally identify this with the cohomology of un plus m quotient by un times un. Right. So right, so you get these classes, and I already told you what those are. They're just Chern classes with two pieces into which your bundle decomposes. Well, let me just go full circle and tell you what this means in terms of the variation of part structures. And I'm going to call it a lemma, but it's really just bookkeeping. Is that if, again, X is a Coleman observation variety, let's say smooth. And I have this polarized C basis. Then, well, what it means is that if I were to create the corresponding complex vector bundle with the underlying smooth manifold, then as a bundle in differential geometric sense, so an SC and DT bundle, this will decompose. The direct summas are labeled like here's what you sum into the weight. Let's say this was a weight that I can. And then, well, what are these invariants that I'm producing? Well, CI of rho L, well, they choose the sign correctly, will be just the eigenvalue class of the sum of all the even parts of this position. And correspondingly for CI part of well, because the variation of part structure is this more finite, this finite decomposition. But if I just remember this Hermitian representation, then I only remember altogether the parts where my polarization is positive definite or where my polarization is negative definite, which are just summing together even at one parts of the decomposition. So all in all, if my option is that if I have a representation into this Hermitian group, then I get these natural classes of cohomology, which remember some shadow of some data associated with it. Right? And again, this one just an elaboration of how you construct this isomorphism. So this is the picture which we have over real numbers. Are there any questions before I move to the p-adic?
I was just wondering, can you say, so this continuous cohomology, is that like, is that some sort of ring of characteristic classes for certain types of bundles?
Right, I don't know how to say it super cleanly. I think really the universal code for characteristic classes would be just the abstract cohomology, perhaps stable. Well, maybe based on that and that, well, depends on how you want to turn it up. Really, I put continuity here just because that's what I know how to compute it. I think that really the kind of formally just ask for a universal class of stable under pullbacks, then this would live in just abstract group cohomology. But I'm pretty cool that I run a continuous class characteristic. And in some other settings, it's very interesting to look at discontinuous cohomology. Such as these term assignments and invariants of local systems, they are discontinuous. Yeah, but I don't know if they already satisfy a statement. So here I showed this for X1 is very easy.
So I was just wondering if you could elaborate a little bit on why the product is equal to 1, because you explained that was, yeah.
Right, very good, yeah. So how do these term classes arise? I'm saying that whenever I have such a representation, I get a rank M vector bundle and a rank M complex vector. Right? But you see there's some, it's not a random complex vector bundle, there's direct one. It's a bundle coming from a complex representation of the fundamental group. So it has a flat connection.
But I was just wondering if do you see that over the whole continuous? Is that why it's over the whole continuous cohomology and not only over like when you pull back to a discrete group?
Oh, I see. How do you see it for oh, I see your point. Right. Sorry. Right. Maybe it's not a full. It's an output of the computation. Maybe it's more of a. Right. I don't know if the one-line explanation why it's still true before you restrict. You're right. Technically, what I said is only a statement after a restriction to this group. Okay, great. So let me try to set up an analog of the story in the p-adic case. And there I think, well, this continuity will be more important. Let me for now just stay in topology or in complex geometry. So suppose I have a topological space. And suppose I come from then suppose I have a representation of the fundamental group, almost as in that stuff, but let me assume from the beginning that it does preserve this legal balance. Although there is an analogous theory for QP coefficients, which is it's almost the same. If you're interested, I can tell you later what it is. So suppose I have such a representation. Never mind yet where you would ever find such a thing. So suppose I'm trying to define some corresponding invariants in cohomology of X. Well, let me again look at continuous cohomology of UNCP. Again, I didn't have to, but in a second I'm going to move into a setting where this will be forced. And so what will be the coefficients that I'm looking at? Well, here this is a pro-finite, well, essentially pro-P group. So its continuous cohomology is most interesting if it only involves P in the coefficients. So let me look at QP coefficients. So then, well, this naturally maps back to the cohomology of the fundamental group of the state coefficients. Just use it as a degree group. And then I can map it to the cohomology of the logical space. So you see previously I said that the goal for me is to produce interesting classes in the cohomology of this universal group. But now, how does the cohomology of this group look like? So there is a p-adic analog of Vanessa isomorphism called Lazar isomorphism. It says that this cohomology turns out to coincide with the cohomology of the Lie algebra of GLM. Just in the purely algebraic sense. And again, maybe this is not so strange because this is you see this p-adic Lie group, and I'm interested in cohomology with rational coefficients. So if I were to restrict to an open subgroup, the restriction mark in cohomology, at least we know a priori would be an injection because I'm restricting to a finite subgroup and I'm doing rational coefficients. But the data of an arbitrarily small open subgroup of p-adic Lie group is exactly the data of its Leo. Maybe it's also strange. It's recorded by the Leo. And then this I can calculate. And for instance, it's the same as the cohomology of the corresponding Lie group G on C as a topological space. And it's just the same as the it's turns out to be generated by n classes living in odd degrees. Ranging from 1 to n. So whenever I have a representation of my fundamental group, I get natural classes. I'll introduce elements. So let me call the equalization. Just label it like star. So Li of rho living in odd degree cohomology of x, defined as the full x of Li over this map. Are the ultimate Lazar classes of my level. Oh, that's great. This representation. All right. So I'm following the same pattern as what I do over the real numbers. So this is the I was able to produce a class of group cohomology using a electricity class of representations valued in that. All right. So let me tell you how you might think about these classes first. So the very first one of them, so I'm telling you that if I start with a representation of my fundamental group into GL and MCP, I'm getting classes in degrees 1, 3, and so on up to 10 minus 1. So what's the first class? This will be very similar to what appeared in Vanstock, but it will be complementary. So I get some class in degree 1, so I know that rho gives rise to the class in 1 row in first cohomology of my space with coefficients in 3D. But it turns out that, well, it's essentially forced that this is determined by this is recovered from the determinant of this representation. And so the determinant of my representation is an element in ZB cross. Right? It's homomorphism from my fundamental group to ZB cross. But now here in the p-adic world, on ZB cross, I have a well-defined p-adic logarithm. Because here it's a range where well, the logarithm series converges. So I can get out of this a p-adic number, a rational p-adic number, and this will be known. So well, this is not so shocking once again. What I said at the beginning that homomorphisms from fundamental groups to abelian groups, they're just Petrov cohomology. But I also claim that there are these higher classes in degrees 3, 5, and so on. So what can you say about them? Before I say anything about them, are there any questions?
That's a stupid one. So it's impossible to leave these classes to integral one.
This one happens to be possible. I think for other classes, at least I don't see a reason because somehow when you're constructing them, in either constructions by Lazar or another one, which I think will come up, they sort of are produced by some rational procedure here for integrating cohomology classes from a Lie algebraic. It's very interesting to look at integral classes. You could write down interesting integral classes, even with non-typical coefficients. Okay. I don't really have anything interesting.
I'm just curious, is this Lazaric isomorphism related to the same formal group clause of Lazar?
It's the same Lazar, but I think I don't think there's a logical relation, but someone should correct me. I think it's he naturally he was interested in formal groups that was interested in p-adic. Maybe Phil would know that. It's definitely the same as Michelle Lazar. sorry, I should make it clear, he probably didn't endorse this, no, this name. I named it after him because it is more. What can you say about higher classes? So let me show you a result which is not very reassuring. That suppose that, again, this makes sense for any topological space. Suppose my topological space was an algebraic variety, important discrete one. But then, in fact, for any representation, the corresponding classes are zero when I larger than. So this, of course, this cannot be true for L1 because I basically told you that any integral class here arises as a low-order class of something. But in higher degrees, they're all zero. But, well, I haven't told you this, but they're definitely not zero universally. If you evaluate this in the other topological spaces, there will be no zero. I guess as will be witnessed by what I'll say next. So this is some kind of restriction on the topology of algebraic varieties. What we emphasize is just C point. This is some restriction on the topology of algebraic varieties.
It's sufficient to be just small.
It doesn't need to be broad. What's important is that the weights in your core structure are all positive in higher degrees. On singular varieties, it's definitely false. You can make any fundamental group, any group fundamental group of a singular variety. Find it. All right. Tell me why I'm actually interested in those things. Because there is something you can do with these p-adic classes which you couldn't do with complex or real classes. So you see here, I thought that my input is going to be a topological space. But now it actually makes perfect sense to take as an input some more arithmetic function. So the x is any scheme in algebraic sense. Then it still makes perfect sense to talk about Z local systems. And it's very interesting as well. They're very interesting examples. So by a Z local system, which this is the local system which plays a role in Anna's song. So suppose that L is the local system one. So by definition, this is the same as continuous representations of this fundamental. And then, since I started with a continuous cohomology class, it just verbatim makes sense to associate to this current classes of I over L, which now live in etale cohomology objects. Because continuous cohomology join the C maps to the continuous cohomology of the fundamental group, and that maps to the cohomology of things. So I produced some invariants here. I'm sorry, by the way, when did they finish? Did they start at 40 or 35?
I think 40. What? 40.
40. Yeah, okay. So I have another comment. Yes. Right. Great. So whatever your x is, it could be, for instance, a scheme over Z or an algebraic variety over non-closed field. You will get these interesting ones. All right. So what can you say about them? Here is a result. Let me give myself a little more space as needed. So this is not an all. All right. Well, let me put myself in the following setting. So let me suppose that now x is itself an algebraic variety over a p-adic. Let's say a sweep float. And right, let me even allow myself like somewhere here on. This is leaving over A, which is a finite extension. then what is the receptacle of these cohomologies? So what is this group? Well, even in a degree, what is the cohomology group? What is X over Q? The coefficient Q. Now, I emphasize that here I'm treating X as a scheme over this non-algebraically closed Q. So I'm taking its absolute cohomology. So how does it look like? Well, there's something which you can call the Lue-Pan exponential map. Which eventually goes into n minus first from homology of X over K. And well, in a second, I'm going to describe this map in a slightly special setting. Let me just say that this map is an isomorphism. If n is larger than 1 and x is greater. So the reduction means that either x is proper and it extends to a smooth proper scheme over the ring of integers, or maybe it's open, but it extends there's a smooth proper scheme over the ring of integers such that x extends to a complement to a horizontal normal velocity. And so, well, where does this isomorphism come from? Under these assumptions. So let me assume that they are satisfied. If you contemplate the Cauchy spectral sequence, you'll learn that this cohomology is just the first cohomology of the Galois group, here A, decay to for the Galois group. With relations in n minus first cohomology. So a priori, there were two other cohomology groups who could contribute to this HN, but under these assumptions, they don't contribute. And now, well, whenever you have cohomology of the Galois group of any p-adic field group coefficients in any p-adic Galois representation, you can map it to the cohomology of the same representation with coefficients as it would be derived. Right, to be derived with some huge QB vector space with a Galois action, but then it's a consequence of the Dirac comparison theorem that this Galois cohomology group can be calculated to be the n minus first norm. All right, and under this assumption, this map, the bottom map happens to be an isomer. Right, well, this map is always divided, if you're maybe not an isomer. So, in other words, if you started with a CP local system on a variety of a p-adic field, or it's the same heat usually, I'm producing some natural drum cohomology class. So what are they? And so here is the computation that we can do. So let me, well, I promised that I would tell you, well, how would I even come across interesting representations of the fundamental groups? Well, with the one example in Aristotle, it was these local systems of Chamorro varieties, and sometimes they were geometric origin, they came from a local cohomology. And this is the setting I want to be, although it could be made more general. So let me imagine that I have a smooth proper family. This vertex is itself smooth proper over.
Okay, I ask something. So can you imagine where the good reduction in velocity calculation?
Oh, yeah, very good point. So here it's being used twice, but for the first time, in the social assessment sequence, well, for instance, a priori H0, HM might contribute. But it would mean that there is some Galois invariant quality plus. But if my variety is to reduction, then this Galois representation is crystalline, and the eigenvalues of convenience in the corresponding prime module are all not equal to 1 by rate invariance. So there can be no invariance. And likewise, well, for a software argument, it doesn't use the reduction H2. And also, to prove that this map is an isomorphism, I think you need to know that the variety is reductions. Here I'm saying that there are no non-trivial extensions of QP by this Galois representation which are wrong. The kernel is not with the exact wrong extensions. But this top map is always wrong. You just have to say the words in the right order. All right. So suppose I have a smooth proper scheme ability, where the variety under which my local systems live is the generic. So if I have such a thing, then just passing the generic fibers, I get smooth program, which I'll call FK. And I can look at its etale homology in something. What does it look like? So this is the TP local system on the generic. And so yeah, to define this, I only need a smooth proper map on the over K, but for what I'm going to say, it will be important that it kind of reduction in this. So this is my main source of TP local systems. Family of varieties defined over K. And the fact that it's defined over K is reflected in the fact that I'm getting a local system really defined over K rather than just the topological representation, rather than the representation of the topological. So then I produce from these classes Li of F, which is just the class with the corresponding representation. What I'm doing this degree of topology, which I can map to the previous degree of topology. And again, since I assume that it was a reduction in degrees when I is larger than 1, this is really a lossless passage that is not as nice one. So I produced for you some previous degree drop topology. So what are they? Let me move this slightly. So it turns out that those are not random classes. They're always classes of algebraic cycles. And here's what they are. So it's a sum over all here in negative integers of the I minus first term character of the m piece of the fourth decomposition on this. So let me parse the formula. Let me first of all finish writing this formula and then parse it. So what am I doing here? I have my smooth proper family increasing error. I can look at the relative cohomology. So I'm looking at push forwards of degree m differential forms. And again, well, maybe it's a good point to cover this. So over complex numbers, it will be exactly the pieces of the fourth decomposition. And now when I say each of these is a vector bundle, I take its I minus first term character. So this is, it's actually an algebraic cycle tensor cube, but I'm just going to look at its realization in draw. And then I'm summing these with the weight m, with m is the key. And then there is some correction derivation. Okay, and some scalar derivation.
You have this cohomology of phi1 of x found in the cohomology of x.
Right. Yeah.
What is that?
Yeah, good point. It's let me say it in topology. So over x you have universal cover. Right? It's a cover with the Galois group phi1 of x. Whenever you have a cover of topological space for some group, the homology of the group maps to the homology of the space.
I see.
For instance, just standard bar complex of the group homology maps to the check of this cover. And I claim that the same makes perfect sense. It's all cool. Right, that second map shouldn't depend on the local system. Just depends on the space. So, well, let me keep this formula. So,
so Li is supposed to be with the 2i minus 1.
Right, it's in degree 2 minus 1, but it's in
The third class, not even.
It's not going to be 0 because the map of your geometric homology is 0 because it's not going to be all together. So it's going to pass the third color. Oh, sorry. I want to make comfortable with the whole thing. It's not the one that I want. First of all, well, how suspicious should be of a statement of such form? So I started with a ZP local system. I take these invariants produced by this kind of formal construction of some group cohomology classes. And I'm telling you that this is something having to do with these Hodge bundles. Well, I'm saying that this is not strange because secretly these Hodge bundles can be recovered altogether from this local system. So each vector bundle we recover by a basically by a certain p-adic comparison theorem from this kind of etale cohomology information contained in L, I can recover the book. But the point is that this particular expression is recovered by this characteristic class. So
okay, just to make sure, like in this case, your etale cohomology has a K vector space structure.
right. Indeed. I think I don't know if I need other construction of this K vector space structure than just producing the map and checking its isomorphisms. I mean, for instance, in degree 1, when n is 1, it will, I think, map subjectively into this K vector space. Oh, sorry, that's correct. It will map onto this K vector space, and the image will be a K vector space, but I think the kernel will be a QP vector space. I also I don't see any canonical. I think it's more basic. Okay. So I'd like to think of this as being parallel to this complex computation that I'm saying that if I have a variation cross structure, I have all of these vector bundles, but then my characteristic classes of the monotonic representation that recover these combinations of even or odd parts altogether. And here I'm saying that if I just have a p-adic monotonic representation, I can recover this strange combination. And this is sort of, in a way, this is more kind of interesting than maybe, anyway, so saying it's sort of a reflection of the fact that in the endpoint theory, often your p-adic local system on a variety of QE, it's kind of as good as a relational construction in a sense that it remembers as much data. And this being one reflection. And another essentially numerological comment, just looking at this formula, is that the fact that the m term appears with multiplicity m is very important. I just summed up these classes with equal weights. I think I've gotten 0. Because Chern character is additive in Schrodinger sequences, so this would be the Chern character of the whole Durand cohomology. But this vector bundle has a flat connection. But because different pieces of the Cauchy composition contribute to different weights, this has a chance of being.
Yeah. Sorry, so for this map from H star I1 to H star F, is it possible for your theorem 1 that some of these L classes are not 0 in the H star I1?
That's a very good question. A posteriori, I think it's impossible, but I don't know. The only the proof of this theorem which I have, it doesn't show this, but there is a very unsatisfactory maneuver of going into or comparing this to complex characteristic classes, which does show this. So I think it's true, but for not very satisfying reasons. But
sorry, can you repeat what
the question was, the theorem is saying that the image of Lazar's classes all the way to cohomology of X was 0. The question was whether it's 0 already in cohomology of the fundamental group. I think it happens to be true, but I don't have a good explanation.
Are there any general properties of that?
Not that I know. I think it's often not in there. Often if you have, probably somebody would know a good example right off the top of their head, but I think you're often your fundamental group is larger cohomological dimension than your first.
I think you already said this, but could you just say again what the map is doing to the H star type?
Oh, yeah, sure. Let me write it down. So this is just the logical setting, but then in the top setting is analysis. So I have the universal property. This is the final line. So for instance, it means that there is a classifying actually classifying a space in the like a full back homology. Is it here?
Yeah.
Okay. All right. So let me, in the remaining 15 or so minutes, say something about the proof or how this computation goes. So we need to use some language, which it will be sort of well, it will require some data training approach, but I'll try to say formally what the properties of all the objects are, even maybe the literal definition wasn't quite make sense. I'm trying to study the p-adic local system of p-adic varieties. And there is this very helpful idea in p-adic push theory that you should trade the complexity of being a local system for a simpler object, which is a vector bundle, at the expense of getting this vector bundle to live on a more complicated space. So if I have any algebraic variety over E, then attach to well, this was defined by Fargues Fontaine, but I think really in this generality, they kind of the point that you should consider this was made by Schultz. There's an object called f sub x, and I'm going to tell you where this object lives. So it's the part of the curve. So it's you're going to think of it as geometric object, but I'm going to think of it very formally. It's a function from perfect weight spaces with QE. What's that? Just actually. And let me write down for you a definition in case you thought about these things before, but otherwise I'm going to tell you what both you need to know. So it's the product of the diamond corresponding to x, or the diamond corresponding to QP, multiplied by the Frobenius of the diamond corresponding to x. So what this object is trying to be, so let me tell you that I'm going to, even if I doesn't quite make sense anymore, what this object is going to you, that it's some object of which it makes sense to talk about etale cohomology of this object, and it makes sense to talk about vector bundles in this object. Because we know what both of those things are in perfect weight spaces, and we can just formally extend this to arbitrary stacks in perfect.
So please, how the second formula is related to the first one?
Sorry, the first one is explaining what type of object this is. But I'm saying, well, both of these objects are also this type of this shape. Okay. Let me say it this way. So, okay. Both, well, X diamond and QP diamond, they're functors on characteristic P perfect weight spaces.
I see.
But it's already multiplied by QP diamond, there's everywhere chosen until over QP, which is why it's living over QP. That was the question. Yeah. So let me allow myself, getting late, to draw a picture that this FFX is trying to be a product of X with spectrum of QP. But this is just a cartoon. I'm going to tell you mathematical statements which are relevant. So here are the properties. So again, if you think of this as a device for studying local system domains. So the first property is what's the relation between the local system domains. That I told you that it makes sense to talk about etale cohomology of this, in particular, it makes sense to talk about finite etale covers. So etale fundamental grid of this object, just the profinite one. It's a product of the etale fundamental grid of X and the Gaussian grid of P. In that sense, it does behave like a product. In particular, if you have a local system on X, so a representation of this fundamental grid, you can create a representation of this grid. And then, so I claim that out of a local system, one X, you can create via the map onto the first projection, which I'll call phi1 star. So this is a local system on the part of the curve, and then I can translate with the structure. And so this is going to be, I'm going to call this a vector bundle on my card. This operation doesn't lose any. What we teach you is that if you're interested in cohomology of this radial local system, then this vector is isomorphic to the cohomology of this corresponding vector. But now in particular, there are zero cohomology are isomorphic. So zero global sections of the local system are the same as global sections of the vector bundle. And this means, since this function is compatible with tensor products, that this assignment algorithm to AO is fully free. So I don't lose any information about my local system. All right. Which is maybe, you could try to loosely compare this to a situation where if you have a complex manifold, you have a C local system, you can make it into a complex vector bundle on the same manifold. And there, this will be a procedure which in general loses information. But here, I sort of tend to do a structure sheet on a larger space where it turns out it's not losing. Great. Now, I'm interested in some sort of characteristic classes of this local system. And again, since this procedure doesn't lose any information, I have a hope of recovering these characteristic classes from the scale. So how am I going to do this? Well, this is a vector bundle. So it seems to make sense to consider its chunk classes. But the chunk classes, where are they going to live? So they're going to live in etale, for instance, the homology of this space f of x. So let me tell you what this is. So for any prime l, which may or may not be equal to b. So what will happen if I compute the etale homology of this part of that curve with alike coefficients and perhaps with some take list, just to make it more general. So let me make a cautionary remark that what I mean by the take list. So you see, this is a rank 1 local system on this curve, and there are two meanings for what there are two natural meanings for this, because I can either pull back this autonomic character from X, or I can pull it back from QP. And these are completely different things that are now decoupled. But I'm really always going to take it from QP. So you should think of it as a geometric object living over QP. And hopefully this will be emphasized by the computation of cohomology, that this cohomology is cohomology of X with trivial coefficients, transferred with the cohomology of the download curve with these twisted coefficients. So consistent with my cartoon in this form. Okay, but now how is it related to X itself? Well, I drew this square, but in fact there is a map from X into here. So by using that, well, importantly, this uses that X lives over K, so but it lives over Q. So it embeds it in some sort of diagonal way. And well, we can make it formal if you know what this notation is. But in principle, there should be a restriction map to the cohomology of X. We'll pull that a long time. Oh, sorry. Let this be killed up. And then what is this implicit map? Well, it's just reflecting the fact that X lives over QP, particular cohomology of QP acts on the cohomology of X. Because I can pull back the cohomology class from QP to X and multiply that again. This is just multiplication. And then let me finish with the most important property. So property 4 is how am I going to recover these characteristic classes? Well, it turns out that if I calculated the I-Turing class of this corresponding vector bundle, and now this is going to live in a cohomology of this object with p-adic coefficients. And I'm going to say it only regressional coefficients. P just means that I invert P on the outside after taking ZB. Then it's going to be equal to the product of the class they care about with a certain class which I'll define in a second. So where does this live? This class I care about lives in relatively cohomology. And there is an auxiliary class in the cohomology of the Gaussian group of QP. So this is up here. So where kappa I is certainly plus, it's independent about the homology of the element. Right, so you can completely calculate this group, for instance, using low count exponential method. That's a certain explicit element. So I'm telling you that I have this term class which lives in this funny product of cohomology of X and cohomology of PP, and my Lazar classes are recovered from the term class, and that the term class is just translating the Lazar class of this auxiliary. Right?
This plus kappa is not zero.
It is not zero, yeah, it's absolutely crucial.
Yeah.
It is true. Proving that this is the case for some kappa is easier than this is a formal thing, but then check it's not zero. Right. So, right, so how do I finish the computation from here in the remaining 3 or so minutes? Let me just say this in broad strokes. So far, what I was saying makes sense for any local system. I didn't really use it. My local system came from a finite varieties. And the computation we're going to do is, it kind of makes sense for a general class of local systems called crystalline local systems. But let me just for simplicity stay in this realm. So, why I said that there was some complicated formalism, why would it give me some advantage? It would give me some advantage if this function was fully faithful, but not essentially subjective. Because well, otherwise I just reformulated what will be a local system is. But crucially, on this Fargues Fontaine curve, there are more vector bundles. And there's another vector bundle associated to our situation, is that in the setting of PR2, if L is my cohomology, then I can also look at the special fiber of my family, right? So where K is the residue. And I can look at the relative crystalline couple. O by crystal. So this is the number of crystalline stuff. Same size as in uninstall. And now, whenever you have an F as a crystal on your special fiber of your variety, you also get a vector bundle on this, or just on this Fargues Fontaine. So for any F as a crystal, M on XK, there is a corresponding bundle EM on this fiber, where X is the generic fiber. And now, as you might expect, I'm going to say that the vector bundle associated to this local system is related to the vector bundle associated to this F as a crystal. And this is called p-adic comparison. Crystalline p-adic comparison theorem. Which I think in this language I have been formulated by Young and Emmanuel in the literature. That, well, I'm going to say it in a slightly, not in the strongest sense, but I'm going to say that if I'm going to restrict this EL to the complement the Fargues Fontaine curve in the Fargues Fontaine curve for this X which I embedded diagonally, well, to be 5 means then they're going to be isomorphic. But on the whole Fargues Fontaine curve, there are different vector bundles, and in fact, one is a modification of the other along this X, which you could think of as a divisor. Right? But now, if you have one vector bundle which is a modification of the other along the divisor, you can imagine that their term classes are related. So you know how to relate Ci of L can be expressed in terms of Ci of En. So this expression depends on the type of the modification that we're doing here, and it's exactly this expression, this modification where the small velocity M appears. But since I'm short on time, let me just finish with the final ingredient. Lemma and Collison really helped us with is that in fact for any m as a first one C, if I were to calculate its current possibility associated bundle in the p-adic cohomology, then there is zero for automorphism. So the way you might want to think about this is that, well, I didn't say this, but let me actually write it down here, that the product of this bundle em onto x, some vector bundle on x, which turns out to just be the f isocrystal m viewed as a vector bundle on x, right? Whenever I have an f isocrystal of a special fiber, I can view it as a vector bundle of flat connection into one that can restrict to the generic. But anyway, there it does have a flat connection. So there its term classes do vanish. It's a geometric cohomology. And this is sort of an extension of this, but notably exposed in degree 1. But now you can see how this computation would go. If you control the modification and you control the result of the modification, then you know the answer. So let's. Questions?
Yes, one.
Oh, sorry, yes, I didn't say this. This is the end. Oh, yeah. So it's in the process of the modification. So I'm modifying their basically. I mean, it's if I have the I'm basically modifying. To me, if I have two vector bundles and I'm modifying along the divisor, the difference is some sheaf supported in the divisor. And it turns out that there it's basically a sheaf with operation where this m graded piece appears m times. It's basically a thing of the form. It's really just a reformulation of the observation that if you have etale cohomology of any variety one, and if you transfer it with bigger one, okay, let's say reverse, you transfer it again. Bigger one, it's related to the crystalline homology of the special one. But these things have their own Biedermann class lattices. And it turns out that these Biedermann modules are isomorphic, but Biedermann plus lattices are different. And the defect between those lattices is exactly expressed here in the quote.
So does that mean like in a theorem 2, and it does not have to assume geometric setting?
Say again?
Like in theorem 2, you don't have to work. So you can work on any tracing local system.
That's right. That's right. I just stated what you said.
And also kind of wonder, like, what's the definition of a etale book for Fargues Fontaine?
Well, just in terms of the finite L corpus, can you define what a finite L corpus is? Well, it's just the category which we define as a limit from all corpus space. Yeah.
Some bounds conditions for it.
Very, very good question. I do, yeah. It's, so here you could sort of go back to the complex Miller inequality, but it turns out that it's actually true for, well, since we asked, let me state a proposition that if X is a curve over P, it's true for a curve. Okay, so suppose I have any ZP local system. Then, well, since it's a curve, there's only interesting classes in the degree 3. So I said third cohomology is the same as second direct cohomology, so this is just PP. So it's a p-adic number. It turns out that it's always an integer. And well, if I didn't mess up the sign in my convention, and I didn't tell you what the convention was anyway, then this is always an integer. And it's always between 0 and g minus 2. But ultimately for the same reason as in complex geometry, because it turns out that etale, oh sorry, I should have this is the rank 2 local. Because attached to this there is a semi-stable rank 2 heat one. I mean, yes, it's a pleasant computation, yeah, for instance. And if you have some, say, family of right, if you have some family of elliptic, well, some say there are linear varieties for your base, you can write down this formula. And for instance, you can always prove that there is always going to be this number is well, on a curve, there's always going to be non-negative. You can prove it out. It's coming from very exposed to it.
That's okay. There's one question saying this formula seems like all you kill off all of this term, right? By multiplied by I minus 1 factorial. So it's kind of looks accelerated like it's.
Yes, I should say it's not a completely clean experiment because I decided to choose this convention for a lot of other classes. I'm getting this formula.
Yeah.
I don't think there are any, but you see this integral structures. Well, right. You see, both the homology here have integral structures. Right, coming from here from singular homology and here coming from algebraic cycles. But I don't see any reason for them to be compatible under this lockout exponential. I don't think this shows that this is a CD code. This is right.
I was wondering if you could say a little bit about what goes into the proof of the Q1 law.
Oh yeah, it's sort of the idea is that you could so we have this as crystal, and we're also going to geometrize this function. So you can look at the stack, which I'll call xk iso. It's a stack over qp, such that vector bundles on it are either crystal from the special. On special line. You can imagine what the thing could be constructed with a drama stack of yours. And then it turns out that there is a map from the Fargues Fontaine to this stack. So the pullback along it takes the vector bundle corresponding to M to this EM. But then you can compute what this map does in etale cohomology. And it turns out that it factors through DT. It's ending up in etale cohomology of X, tensor etale cohomology with QP. And it turns out that it factors through the etale cohomology of the special fiber, tensor etale cohomology of QP. But then, which is maybe not so strange because it's really only depends on the special. But then it turns out that the etale cohomology of the special fiber by weight conjectures only lives in degrees 0 and 1. Because higher degree cohomology have no doubling there.
Sorry, I'm confused here. So isn't it, I thought that your L is P now, no?
Sorry, the statement I'm saying is true for any L.
But you're interested in the case when
both
L is equal to P.
That's right.
So what is the what?
So I'm saying that this map factors through only the special fiber,
which is in Cartesian.
Yes. So L might be P. Maybe L is equal to P, right?
But then what do you say about weight conjectures?
It's not true because it's how easy cohomology, it's for Venus invariants of crystalline cohomology. Or kind of but there's still no ways. No, I think that is So the structure is that you first prove in general for any variety that it factors for the group. Then for a smooth proper variety for K, we prove that this group just has nothing into it starting before. But wait.
That's one question. It's like in the complex setting, you have these like Kellogg inequalities that like about the slope of like one Hodge bundle in terms of the slope of the previous one. Is there some analog of that here?
Are the consequences of the semi-stability of the Higgs bundle?
Yeah.
If they are, then yes. Whenever you have a Z-equal system, there is a corresponding Higgs bundle, semi-stable. So whatever algebraic consequences of semi-stability you have them here. But if it's a more complicated, it's some more analytic reason that I don't know, but I've never read such finer.
It's these semi-stable lambda moduli.
Yeah. Right. Then it should be that.
Well, there are no more questions. Let's thank speaker again.